Welcome to the August edition of the Liftoff webinar series. The Liftoff webinar series is brought to you by LIFT, Lightweight Innovations for Tomorrow here in Detroit, as well as the Michigan Manufacturing Technology Center. We are pleased to bring to you Detroit engineered products today to talk about weld optimization and some fast computer-aided modeling techniques. As you guys know, we are here each third Thursday of the month at noon Eastern time to talk about small and medium-sized enterprises and some of the lightweighting innovations that they are working on, and we are proud to have them all as part of our LIFT network. A few housekeeping items I'd like to go through before we hand off the presentation to a couple of folks from DEP. The first is please put your phones on mute. I want to make sure there's limited to no background noise during the presentation. If you have questions during the presentation, please use the GoToMeeting chat function and send your question to the organizer. That will come to me, and then we can facilitate the Q&A at the end of the session. And as a reminder, each Liftoff webinar is being recorded, and they are all posted on the LIFT website for future viewing. So if you want to go back and check on something you missed, or if you want to send the link to a colleague or coworker of yours who wasn't able to make it today, they are available on our website. So this one will be available probably early next week to do that. So you'll be able to go back and look at all the previous sessions that we have had in the past. A little bit about LIFT. We are a member of Manufacturing USA. Manufacturing USA is a network of 14 innovation institutes established through the federal government. We are public-private partnerships, so we receive some funding through the federal government as well as industry partners. Each of the 14 institutes has a different technology that they specialize in, but that we all operate in the same three kind of buckets. The first being technology development. We focus on R&D in our specific technology. Ours happens to be lightweight metals. We have a number of technology development projects underway. You can visit and see what those are all about on our website at lift.technology. We also aim to transition that technology into the marketplace, because what good is investing in and creating these new innovations when they are not transitioned and being used in the market. Finally, the third piece is education workforce development. We want to make sure that the pipeline of talent of people, whether it be students or incumbent workers, they all have the knowledge, skills, and abilities to use the innovations and technologies that are coming out of these Manufacturing USA institutes. So we are based in Detroit. Our mission is a broad one, but simple at the same time. We're revolutionizing lightweight metals manufacturing through innovation and education. We have, as I mentioned, we have nearly 20 large technology programs that are underway. We just announced the completion of one earlier this week, where we work with a member of ours, Huntington Ingalls, and a team of LIFT members, industry and academia, to solve some issues when it came to welding sheet plates together to build chips. So we wanted to reduce the distortion that takes place with the welding process, and we're able to do that. So you can read more about that on our LIFT.technology website as well. Also want to mention that I think he's now in his second month as our CEO and Executive Director, but we have Nigel Francis on board as our CEO and Executive Director. So if you have not had the chance to meet him, please visit us in Detroit and do so. We'd be happy to have you here and show you around. You can also follow us on the social media channels, Twitter and whatnot, at News from LIFT. And you can also feel free to give us a call, ask us any questions that you have. We are home here in Detroit to a 100,000 square foot R&D facility. We share it with one of the other institutes, IACME, that focuses on composite materials. They are actually based in Tennessee, but they have a number of folks here working on their automotive scale-up research facility. But as you see on your screen, we have a number of large pieces of production-sized equipment that are available for use for R&D work, for prototyping work, for small batch manufacturing work. We also have engineering services. We also have reverse engineering services, and any number of things that you can that we can help you with, from project management all on down the line. either in-house or we can help you find solutions across our network. So please reach out to us, come visit us if you have not done so. We would love to be able to show you this wonderful facility that we have here in Detroit. As I mentioned earlier, we are brought to you by also by the Michigan Manufacturing Technology Center. They are a member of the MEP network, the Manufacturing Extension Partnership, through the National Institutes of Science and Technology, NIST. They have been a member of LIFT from the very beginning, but they also offer solutions to manufacturers of all kinds, not just in metals or composites, anybody that makes anything. They are a resource here in Michigan for a number of the services that you see on your screen now, from cybersecurity to skill development to research services on down the line. They are based in Plymouth, Michigan, and we are happy to have them as a partner to help us bring to light some of the innovations that are taking place with the small and medium-sized manufacturers. So glad to have the center here with us. So without further ado, I'd like to introduce Detroit Engineered Products to kick off their session of the webinar today. I know they have a number of people that will be presenting, at least a couple of them. So I'm going to hand it off to Radha first, and they can introduce themselves as they get going. But I will hand off controls of the webinar to him, and we can kick it off with DEP.
Great. Thanks, Joe. Good morning and good afternoon to everyone. Thanks again for joining this this session on weld optimization. The title of the topic today is weld optimization and how to do fast CAE modeling for modeling the welds to reduce the time required for modeling the welds, and also to minimize the welds, which has manufacturing cost reduction objectives, and also to overall reduce the product weight, because welding plays a key role with respect to the structural performance of any of the products that we all design and develop. So today's topic is going to touch on the CAE modeling techniques of the welding process, more from a product design perspective, and also at the same time how to lightweight your product and reduce manufacturing cost by minimizing the welds. Now, with that having said, very brief introduction to Detroit Engineered Products, or in other words, DEP. We are a consulting services company supporting all different industry verticals, and we are also a software development company. And Meshworks is our CAE platform, which is used by several customers in the automotive and non-automotive space. And we also provide engineers to be part of your design and development team. And we also do hardware-based product development involving all types of manufacturing processes, castings, stampings, etc., on different types of materials. We are a company, global company, with different customers with different offices in different geographies, and supporting automotive, aerospace, heavy equipment, and other industry verticals. Globally, 425 engineers with a cross-section of advanced degrees and bachelors. This is who we are, headquartered in Troy, Michigan. And all our solutions are aimed at how to reduce your product design and developmental time, while at the same time minimize weight and cost of all your products that you design. So this is what our entire solution, whether it's our software solution or our consulting service solution, aims to provide to all customers. Today's agenda, very briefly, we will be touching on, from a product design standpoint, how to model all the joining techniques in your product, It could be a seam weld, it could be a spot weld, it could be adhesives, all kinds of joining. How do we quickly model them in your CAE models? There'll be one topic involving different types of models, shell element based models for thin walled structures, and cast members model with solid meshes, etc. We will touch on that, and we will go into sufficient detail on modeling all the heat affected zone that arises out of your welding process, and then also crack propagation modeling. We will touch on all of that. And then comes the second half of the presentation, touching on how to parameterize all your design at a CAE model level. So the parameterization is applied to weld lengths, weld pitch, etc., and also all other geometric parameters of your design, like wall thicknesses, shape changes, etc. So we will talk about how to parameterize effectively all your CAE models, and then subsequently how we would optimize the entire product design using the parametric model to achieve a lightweight design, and at the same time with reduced weld count or weld length. So this is what is going to be the agenda over the next half an hour or so. Following that, we would be very open to answering any questions. First, talking about different types of CAE models. If it's a cast component, the tetrahedral meshing is a very common industry practice. You can create all your component models very rapidly with Meshworks, of course. Very complex geometries, creating good quality finite element models of the castings is part of your design and development process. If it is sheet metal, modeling all the sheet metal assemblies using shell element modeling. This is another common industry practice to capture the structural performance of all your sheet metal components. And if they are plastic components or thin wall castings, modeling them with the so-called mid-plane shell element representation with varying wall thicknesses to account for all the draft angle that is there in your structural design. This is also a very common industry practice. So across the board, whether it's sheet metal, castings, plastics, or fabricated structures, in general, the modeling methodology could fall in any of these categories. And of course, there's one more category called hexameshing, which is also very common industry practice to model components, especially highly nonlinear components using hexameshes. Then comes the very, very important part of joining all the component finite element models with appropriate weld elements. So if it is a spot welded structure, like a typical automotive structure, then the spot welding is the main process on the body in white. In that case, the modeling of the spot welds in a very quick, rapid way is very important. So we will show you through some live demonstrations how spot welds can be created very fast. And if you have adhesives as additional stiffening and strengthening joining technique, we will be showing how adhesives can be created very rapidly throughout your entire model. Then comes a lot of the seam welding type of application. When you have sheet metal fabricated, how to join the different components using seam weld elements, where the technique is a little bit different. So in general, the technique of finite element modeling for a spot weld versus adhesive versus a seam weld could be completely different, and one needs to be in a position to be able to model all that very fast. And of course, assemblies could also be driven by bolted structures, as we all know. There also you need fast modeling techniques. Last one, but not least, where you have assemblies packed together, making contacts with each other. They're also being able to do the contact modeling quickly is necessary. This is another example of a heavy equipment, heavy machinery component fabricated and welded together. The detail of the welding, where all the weldment should be modeled in detail with solid elements with complete node-to-node compatibility with the two parts that it is joining, all that plays a significant role in getting the good fidelity of your analysis results. So the fidelity of your model with a high degree of confidence in your predictions, whether it's crack propagation or crack initiation, all of that calls for how we model the welds in all these interfaces. And of course, at the same time, when you want to put in a lot of detail, how do we do it in a very fast, effective way? So this is what is going to be shown to you, the ways to do this kind of joining very fast. Talking about modeling the detail around your welds. For example, this is a seam weld. This brown and purple elements represent the seam weld. And then right next to it is the heat affected zone. The green elements, the blue elements, and then the surrounding toe region, the bottom toe region and the surrounding end zones on the parent material, they need to be modeled in a very, very specific way, because this captures the heat affected zone with a completely different material property due to the heat that is generated during the manufacturing process, during the welding process. And modeling that region with sufficient detail like this is then going to help you with a high degree of confidence predict the stresses, the crack initiation, and the subsequent crack propagation in an effective way. So I'm building the story here as to the need for modeling all these interfaces in a very detailed fashion. And another snapshot of another type of joining where, again, the heat affected zone is being modeled in a very, very detailed fashion. So at this point of time, I'm going to turn it over to Ray, and Ray will show some quick demonstrations that will illustrate how fast one can do a lot of this kind of modeling of the weld.
Thank you, Radha. Hello, everyone. My name is Ray Cheney. I'm Director of all the software support and some of the product development here at DEP. And I'm going to quickly show you guys how to do some of the welding, the quick welding between two sheet metal components. So here we're going to show you how we can quickly select a couple of nodes here on the screen. Yep, this is going to be for the spot welds. So now I basically just specified the connecting parts. I have 3 connecting parts here. And I'm going to use a method for shell gap method. And I'm going to say realize. So you can see very quickly, Meshworks has nicely created the weld element. This is a 3D weld element here with the 1D connections connecting the surrounding components. And we have a few different types of welds. We have the ACM shell gap weld. I can say reset, and just to show you a couple of weld scenarios. We have an RSM weld that we can create. Select the nodes once again. And say realize. So this is another weld type here, to where we have the 1D rigid created by one link rigid that's linking all the 3 rigids together. I'm going to say reset, and I'm also going to show you some rigid connections. So this would be like a dyna type of modeling, to where you would just have a rigid connection just linking all the three components together. So now for the next demo, I'm going to quickly move over to the seam welding. So we want to create a seam weld here between these two components. So I'm going to go to modeling and model assembly. Go to seam weld, and here we already have a pre-created what we call a weld line. So I'm going to select that and select this as the master and this as the slave. And for my weld type, I want to select quad elements. And I have a few different options here, but right now we're going to look at how a weld can be created with a continuous line. I'm going to click on Realize, and you can see how the tool has nicely created a seam weld with quad elements that's connecting the two components together.
One comment here, the weld line which Ray showed, it's a matter of half a minute to create a weld line. And a lot of times during the early stage of your product development, your CAD data may not even have the weld information. Not a problem. So one can directly create a weld line using your finite element model representation itself.
So now we're going to switch to a different type of weld to where we can also just have a rigid one-to-one connection. I'm going to click on Realize. And now you can see how the tool is nicely creating a one-to-one connection.
Yeah. Mine is coming.
Yep. So you can see how it's creating a nice one-to-one connection joining the parts together. I'm going to reset that, and now I'm going to show you a different methodology. What we use is called a V-quad type of welding. So when I say realize, you can see that we have a 45-degree angle. And it's basically the 45-degree angle can go in this direction. But using our tool, we can nicely control the opposite direction also. So I'm going to say reset, change the angle in the reverse position. And now you can see the 45-degree angle going in the opposite direction. So for the next welding scenario, we're going to show you how to create a weldment between two solid components. So now, as Radha mentioned, we have the seam line that's already created in our model. So I'm going to select the 1D element, select the master and slave component. And now here, when I click on this, we have a bunch of inputs that we can select from. So here, I'm just going to stay on the flat method. I want to say accept. I'm going to say preview the weldment. And this is with the heat affected zone. Let me show you without the heat affected zone. So it's going to show you a preview of the weldment that's selected for the flat. So you can see that it's basically a straight line going from this point to this point. So I'm going to say reset and change my input to concave. So for the concave weldment, you can see that you have a concave shape here right at the edges. I'm going to also show the input for convex. So now you can see for this weld, you have a nice convex weld that has almost like what you call a radius on the weld. And now we're going to show you a new methodology to where we just created, to where we have the tapered weld, to where you're going to have the converging ends. Now you can see how the tool is nicely creating a converging end on the welds here to help reduce false stresses that you may get in your analysis. So now we're going to basically show you. We're going to preview it. And before we do that, I'm going to go back to my inputs and I can show you how we can nicely control the heat affected zone. I can put here for my heat affected zone for 2.5. Number of layers that I want here for my heat affected zone is 2. I can say preview. and it's going to give you a nice preview of what the heat affected zone is going to look like. So now I'm going to just say realize, and what the tool is going to do is, when it realizes this weld, it's going to nicely create all quad elements adjacent to this weld. So when you basically look at the analysis, you want to basically have good results coming from the weld, so you can nicely predict all your welds and all your stresses very nicely. So you can see how it's nicely creating the nice layered mesh adjacent to the weldment.
One important point to note here is that all the three components here, the two parent components and the weldment, they all have node-to-node connection compatibility. This is one of the best conditions to have for very accurate weld modeling. So the tool does a very effective job of maintaining compatibility of the different meshes.
So for the next demo, here we have a slightly different situation. Here we have what we call a hybrid mesh. We have the tetra mesh here, and we have the hexa mesh here, and we want to have the node-to-node connectivity after joining all these together.
So normally the process of all this modeling, if you use conventional tools to weld, let's say 40-50 welds in, let's say, a typical fabricated assembled structure, will take a week's time, all right, 40 hours for somebody who's, and that is very good at modeling. Whereas with these fast modeling techniques, you are talking about getting the whole welded assembly done in half a day, all right? That's the amount of time compression one can expect with respect to very fast modeling.
So for this scenario, instead of using the weld line creation method, here we have what we call a TET fuse option, to where I can fuse these welds to this hexa model also, and fuse it to the tetra model in one shot. So I'm selecting my weldments as my master, and I can select the multiple slave components. And when I click on create, you're going to see how it's nicely going to propagate through the hexa component and also do a fusing with the tetra mesh, and you're going to be left with node-to-node connectivity in this hybrid mesh. So now that's done, and you can see, if I turn this component off, you can see how it's nicely taking the footprint on this component and also this component.
So now that you have seen how the modeling part of the welds, now let's switch gears to the analysis part. So Joe, if you can transfer over to my machine, make me the presenter. This is Radha. I'll be able to share my screen. Okay. As you have seen from Ray's demos, we showed how welds can be created very fast. Once you have a model like that, then you can carry out all types of load case analysis. Let's say an impact load case like the crash, or a stiffness or frequency based noise and vibration kind of analysis, or a durability simulation driven by stresses. All kinds of load cases, the welding and the representation of the weldment plays a huge role. So if in an impact load case, if a spot weld fails, if it debonds, let's say, all right, then the complete failure mode can change if the spot welds give way. Same way, with respect to the frequency of a structure, can greatly be affected whether you put 100 welds or 50 welds, or which location you are going to weld it. Same case with seam welds and so on. The stresses, crack initiation, fatigue life, and crack propagation, everything is going to be quite a bit dependent on how we model and analyze all the spot welds and seam welds in your structure. And the kind of load cases you may have to be studying also could be quite varied, all the way from, in this example, in an automotive axle, some bending loads, torsional loads, actual road loads, and frequencies for all to keep all the noise and vibration aspects of it met, and all the manufacturing loads. The whole system needs to be analyzed as an assembly with all the weld and welds represented. So this is the analysis part. And when you go down to the details of the analysis, the local stresses around the heat affected zone will be captured very much more accurately and more realistically based on how you are modeling the heat affected zone. So this is where the stresses and the crack initiation and propagation is going to play a very crucial role in the level of detail you put during the modeling phase. So once you have gotten a good degree of confidence in your analysis prediction, then comes the optimization. And for optimization, you need to first parameterize your models, your CAE models. So taking the axle as an example, the axle is made up of several components. And one of the main type of parameters that you would want to introduce are shape parameters, wherein every design feature of your model can be quickly parameterized at the finite element model level itself. And all this is done very effectively within the Meshworks environment. And it can be castings, it could be stampings, or it could be formed tubes. Doesn't matter what is the nature of your manufacturing process. The idea is how to parameterize all of these components by way of their shape, their gauge, their material, etc. And along with that, one needs to parameterize the well length and the dimensions of the wells itself. So now the picture is much more complete when you have the ability to not only control the parameters of the shape of the parts, but also the lengths and the shape of the wells. Okay. So with these items, with these parameters as your tuning knobs, now you can proceed ahead to the next stage of optimization. And your parameters need not be limited only to shape, gauge, material, and joining methods, but it can involve several features like beads, darts, and other structural reinforcements, etc. So at this point of time, again, I want to quickly transfer over to Sridhar. So Joe, if you can give the control to Sridhar, we want to show a couple more demos on how the parameterization, a parametric model would typically look like.
Thanks, Radha. Hello all. Myself Sridhar, and I am a lead engineer for Meshworks support. I'm going to demonstrate you how to create a spot well parameterization. So before going to the parameterization tab, the preliminary request for any user is like we need to convert the weld elements to weld lines. So we have a very good tool here. I'm going to modeling, model assembly, spot welds.
Now, in the interest of time, we can directly show the review of the parameters and not the creation of the parameter.
Okay.
Yeah. And later on, if we get more time, then we can show how to parameterize the,
So I already have a weld parameter created for my door rings. And I'm keeping my model in a transparent mode. And if you see, like they are like weld lines and represented with nodes and a triangular shapes. The circular nodes are represents the 2T wells and the triangular represents the 3T wells. And now I'm going to review the spot weld parameter. And here, if you see, like a user have the chance to minimize and maximize the number of wells based on the pitch and number of wells and the average pitch. So this is about spot weld parameter, and I want to quickly move on to other demo where I'm going to show you a B-pillar auto parameterization. So here we have used a couple of tools to create a quick parameters. For example, a user have to select the inner and outer. So I'm going to quickly review the parameters. So this is the width of the parameter.
So here we are looking at a combination of how we are controlling the shape of the structure, like the width, and then the depth. So you can rotate the view and show the depth of the cross section. So we are changing the depth of the members, and then we are going to show the depth on the other side. And then not only the shape changes, now we are going to simultaneously introduce the parameters on the welding, okay, which is essentially controlling the weld pitch. So zooming in closer, now you will see how the weld pitch is going to be controlled. So the effectiveness of your structural performance, you'll get the maximum juice out of it when you are able to control both shape, gauge, material, and welding together. Then going on to the seam welding, here also we are going to review the parameter and show you how we are going to control all of this. So first we are going to showcase the first parameter, which is the thickness parameter, wherein we are showing the thickness of the bracket. So can you zoom in even closer to one corner? Yeah. Yeah, so go ahead and review the parameter again. So as you can see, we are controlling the entire thickness of the part. And likewise, we are going to control the thickness of the tube as well. So, as we can move the slider, you can see the thickness of the tube is going to be changed. And now there is a more interesting parameter as an assembly. Now we want to change the diameter of the tube, the outer diameter of the tube. And as you can clearly see, we have rotate a little bit down and zoom in closer to the well, a little bit downward. Yeah. All right. And as we move the slider, the diameter of the tube is increased or decreased. And along with it, the weldment also goes for the ride. And also it changes the surrounding part as well. Can you rotate a little bit to the left? To the left, yeah. And now show the animation again. So you can see how the geometry of the bracket as well as the tube are getting changed with the weldment kept intact. And of course, the length of the weld also can be made as a parameter. So now you have the complete control over all the tuning knobs of your product. So Joe, if you could kindly give me control, I would like to wrap up with a few more slides showing how such a parametric model could be taken further and linked with an optimization process. So you bring in all your CAE models into the Meshworks environment, and you parameterize all the shape, gauge, material, and the welding parameters. And using a process integrator like tools like iSight or Mode Frontier, you then start with the design of experiments matrix. And with the DOE matrix going into Meshworks, out come all your analysis models ready for your analysis. And this is where you get all your output responses, like fatigue, life, stiffness, frequency, impact performance, etc. Let's say you're running 100 variations, and from all the 100 variations, you can get the output responses tabulated. Chances are very high that from the design of experiments itself, you can get some very good designs, much better than where you started off with. And you can go one step further, bring in all the responses back to the optimizer and create what is called a response surface or approximation model, apply objectives and constraints, and then you get the optimized design. So this is a process that works extremely well for all medium-size and large-size problems. And now some successful case studies we want to show. What you have here is an automotive cabin body. We started initially on this body with about 860 wells in different locations of the flanges of the cabin. We wanted to look at the torsional frequency of the cabin and a matchboxing mode of the cabin, as well as the bending frequency mode of the cabin, because during the early stage of the design and development, stiffness and hence the frequency is the primary driver of the design. So the goal was to reduce the well count and at the same time make sure there is no compromise on the performance, which is the frequencies, which are shown by all these graphs here. So with this optimization technique that I showed you in the previous slides, the whole project was executed, and at the end of the day, there was a well reduction of about 262, and which directly translated into a manufacturing cost saving. So this is a case wherein you maintain performance and still reduce the well count. So yet another example, this is again an automotive example on the spot welding side. So here, this is the front motor compartment of the vehicle, and I'm showing you the before-after scenario for a frontal crash. What we are interested in, let's talk about the baseline design. In the baseline design, there were about 560 wells, spot wells in this region. And what is important as a response is the pulse, which is generated due to the impact. The lesser the pulse, the better it is to protect the occupant. And these are all what we call as intrusions coming into the vehicle, the deformation happening into the vehicle where the occupant's foot is, 70 millimeter, 40 millimeter, etc., at different points on the footrest and also on the instrument panel. So the baseline design's performance is shown here. So the lesser the pulse, the lesser the deformation, the better protection you can have for the occupant. And now, due to the optimization that we conducted, you can see there is a well count reduction of nearly about 70. So we were able to reduce the weld, and at the same time, we were able to reduce the pulse and the deformation. So this is a case wherein you are getting both a performance gain as well as a reduction in the well count. One more example, and this is the last and final example. So here, this is a seam welded structure modeled in detail, where the main emphasis is on durability. So how to reduce the stresses, improve the fatigue life, minimize crack propagation, rather extend the life through the crack propagation, and at the same time reduce weight. So we were able to meet all the performance targets, and at the same time, there was a 5.5 kilograms weight reduction on an axle assembly that is weighing about 30 kilograms. All right. Off of a 30 kilogram assembly, a significant weight reduction of about 20-25% was achieved while at the same time meeting all the structural performance. So here you have a situation wherein you not only were able to reduce the weld length at all these locations, but at the same time reduce the weight as well. So we were able to maintain performance, reduce weight, and at the same time reduce the weld length. So in summary, with this process of a Meshworks driven process, one can really minimize the time needed to do all of the CAE modeling that is necessary to capture the welding. And you can model it in extreme detail, capturing the heat affected zone, the material property change in all that heat affected zone, etc. And then subsequently, you not only can model it, but you can model it in a very, very fast, practical way. Because at the end of the day, we are all driven by the program timing. So a fast modeling technique is necessary. And then you can also parameterize it subsequently and link it with an optimization scheme, whereby you truly do the engineering in order to improve performance, minimize weight, and minimize the manufacturing cost associated with welding process, welding and in general all joining processes. So this is in essence what we wanted to share with you, and we'll be glad to answer any questions if you have.
Excellent. Thank you very much, everybody. That was that's an awesome presentation. Very cool to see. We did have a question come in. The question is, can you describe how the frequencies factor into the strength of the cab you showed? Do the higher frequencies correspond to less flex and a stronger assembly at all?
Yeah. So in the case of the cabin body, or for that matter, any of the automotive body structure, it's not necessarily that we are shooting for the stiffest body structure. So there is a target frequency that is set for the body structure, like 35 hertz, 40 hertz, or 45 hertz. And that is driven by different considerations. One is the noise and vibration characteristics of the entire vehicle. So you position the frequencies of the body structure so that it is kept away from any of the suspension modes or the powertrain modes. So that is the predominant driving factor in determining what the body structure's frequencies ought to be. And then when it comes to the overall static torsional stiffness and bending stiffness of the same body structure, that to a large extent it is dependent on the frequency as well. But there are separate targets set for body torsional stiffness and body bending stiffness. So both are interrelated. The frequencies and the stiffnesses are interrelated, but predominantly the driver of what the frequency ought to be is driven by the overall noise and vibration characteristics of the entire vehicle.
Thank you very much. As a reminder, if you do have a question, we have a few minutes left. Please use the GoToMeeting taskbar and address your question to the organizer, and we can facilitate the Q&A here. In the meantime, folks from DEP, can you provide ways that we can contact you or reach out to you? Is there a website or an email address that folks can reach out to you guys at?
Absolutely. So it's www.depusa.com. And the direct contact is John Gelmisi. I believe it is being flashed on the screen. Or,
Can you make me John Gelmisi the presenter?
So we will flash the slide, Joe. You can give the control to John.
Yep, you should have it now.
So you're sharing.
Share your screen, and we'll be good to go.
Okay.
So as John is sharing it, one comment on Meshworks. It has been benchmarked as one of the fastest modeling tool in the industry. Folks may be knowing about HyperWorks and other kinds of products, and we have been extensively benchmarked against those products, and it's been recognized that using Meshworks, the time saving is of the order of 40 to 50% compared to other tools that you may be presently using. So both for meshing and model assembly, and then also subsequent parameterization and enabling optimization, Meshworks is a chosen platform with the tremendous time saving for all our users.
Excellent. Well, thank you very much. I don't see any more questions coming in, but please, I encourage everyone on the call to reach out to Detroit Engineered Products, reach out to John with any additional questions or follow-up you might have regarding their software. We certainly appreciate your presentation today. As always, and as a reminder, please check back to the lift.technology website next week, and you can review this presentation as well as the other liftoff presentations we've had over the course of the last year. And then stay tuned for the third Thursday of each month. We will have a new webinar each of those months. And check your email for the registration link and more information to come. So in the meantime, thank you so much, everybody, and we will see you next month.
Thank you, Joe. Thanks.